Hello everyone, my name is Nagesh and today I'm going to talk about scalable system scheduling for high performance computing and big data. So coming to our paper abstract, so as we all know, job schedulers are the operating systems of modern big data architecture and supercomputing system in the constantly increasing field of parallel computing. So job schedulers allocate computer resources and control the execution of process on those resources. Job schedulers were the domain of supercomputers. As we know, job schedulers were designed to run on massive, long-running computational over days and weeks. Detailed measurements and modeling of this performance of schedulers are critical for maximizing the performance of large-scale computing systems. In this particular paper, a detailed feature analysis of 15 supercomputing and big data schedulers are being reviewed and given. So coming to our introduction, the evolution of computing into the hyperscale data center era has created massive computer infrastructures that can be turned into solved wide range of problems. The operating system of data center is a job scheduler, which decides which tasks are executed on which resources. So it's the main which system that decides what are the tasks that needs to be executed on which resources. Multiple users submit a wide range of computational jobs to be processed on computational resources that include various processing cores, network links, memory stores, storage pools, and software execution licenses. Job schedulers are the key part of modern computing infrastructure. If the job scheduler are not effectively managed resources and jobs, then the computing capabilities will not perform well. Job schedulers go with variety names. As you can see in the mentioned paper, uh, they are known as RMS, Resource Management System, or Resource Managers, or Distributed Resource Management Systems, DRMS. The two main terms, scheduler and resource manager, capture the primary activities of this type of distributed software. The users and the job usually have different resource requirements and priorities. Similarly, the computational resources have different capabilities and availabilities, and these change dynamically as the different jobs are executed. So, in functional model of schedulers, every job scheduler has an architecture with four key features. They are job lifecycle management, resource management, scheduling, and job execution. Traditional high performance computing jobs can be categorized into single process jobs, a set of single process jobs that is grouped together and executed asynchronously, and a set of processes that are launched and executed simultaneously and synchronously. No. So, interactive prototyping parallel jobs have many of the same characteristics of typical capacity supercomputing jobs, but they tend to occupy fewer processors and execute for less time. Because of these mechanism, the job submit to a batch queue with such an interactive queues, immediate execution flags and slot reservation, which enable this because of which it enables an interactive job execution. So as we can see, the majority of big data jobs are very short time critical jobs that execute in a matter of seconds to minutes are independent of each other. High performance data analytics jobs have characteristics of both HPC and big data jobs. In this particular paper, the authors have explored the feature that is necessary to execute high performance data analytics jobs because we need the best of both to beat to the best of both and which can accommodate such jobs. So this paper has made certain contributions. So they are, it introduces the characterization of schedulers into scheduler families and categorizes a set of HPC and big data into these families. It enumerates a set of scheduler features that are important for high performance data analysis jobs and compares the support for these features for a representative set of HPC and big data schedulers. It recognizes many features and supported across the schedulers, but that is a key scheduler feature that not has been explored in much detail is job scheduler latency. It derives a mathematical description for job launch latency. It presents a benchmarking strategy for measuring job launch latency and benchmark a representative set of HPC and big data schedulers. In this paper, it measures a marginal latency and nonlinear exponent of job latency of the benchmark results of the representative set of HPC and big data schedulers. Literature summary. A lot of research has been published on optimizing the placement of jobs into the resource set with a great deal of variety in both the homogeneity and heterogeneity of the jobs and the resources. There has been significant research in how to characterize and model the execution of resources utilization in various algorithms and applications, both as a serial job and as a parallel job. We will overview the most significant literature to differentiate our work on job scheduler performance and performance to enable high performance data and analytical jobs. First, it is worthwhile to address related work in survey and comparison literature. This literature addresses in four functional areas of scheduler, while the feature comparison most closely address the job lifecycle management functionality. There are many papers conducted to choose a new scheduler of an organizational supercomputing or a big data system. The first paper that brought about comparison of schedulers came from NASA in late 1900 when they were replacing a network queuing system NQS batch scheduler at NASA. This work promoted two reports that catalyzed the development of a portable batch system PBS by Jones in 1996. Rudolph and Fulton in 1995 wrote a paper that established a basis of making comparisons between job schedulers and other schedulers that were developed by other organizations. To share supercomputing resources in early 2000s, a number of universities and research organizations were developing technology across this as a computing grid. Among the significant papers and books from the research of scheduling, there were many papers that were brought and written in the area of big data scheduling and jobs. As we can see, there are some examples as mentioned in our presentation. Similarity among big data schedulers by uh, using Mesos, MapReduce, and Hadoop Yarn, which was published in 2016, and more recently, there have been few articles that make comparisons between traditional HPC schedulers, grid schedulers, and big data schedulers, as well as in cloud computing. The comparison examines some subset of features that were considered in service to certain processing workloads, usually real workloads and sophisticated models of real workload. Further, the comparison have been within the traditional HPC or big data job comparison areas, but have not taken candidate schedulers for both. The number of papers that focus on comparing the queue management and scheduling algorithm within the schedulers. There are a lot of papers. So let's talk about the methodology that is described in this particular paper. First, let's talk about the job scheduler. A job scheduler is a program that enables an enterprise to schedule and, in some cases, monitor computer batch jobs. So, it's a program that enables an enterprise to schedule and monitor. We organize these traditional HPC and big data job schedulers into several scheduler families to in common intent and develop among them. So the next topic is the scheduling families. A number of production quality schedulers have been developed over past 35 years to address various supercomputing and parallel data analysis for computer architecture, network architecture, and software architecture. One of the first fully featured schedulers was the network queuing system with batch scheduler, which was developed by NASA in US. HPC job tends to be long running, synchronously parallel simulation and modeling jobs. Traditional HPC families. A portable batch system PBS scheduling family is directly descended from NQS, which was developed by NASA, which was the very first scheduler. PBS portable batch system is a fully featured job scheduler that includes a separate queue manager, resource manager, and a scheduler, which is often used in place of a native PBS scheduler. The new HPC family, a simple Linux utility for resource management, which is also called as SLURM, is an extremely scalable, full-featured scheduler with a modern multi-threaded core scheduler and a very high-performance plugin module architecture. Commercial big data family. So Google introduced MapReduce, which was by the Dean and Harvard in 2008. They released this paper which detailed on how they implemented a map reduce processing paradigm to process data files stored locally on each computer node. The job scheduler was a simple first in, first out scheduler with few features. Subsequent improvements were added by Google based on the required capabilities. Open source big data family. Apache Hadoop Yarn is an in-memory map reduce job scheduler. Yarn is yet another resource management, which is a job scheduler that enables scaling map reduce style job environments to execute efficiently on thousands of servers. It was built to increase the processing speed and scalability of Apache Hadoop MapReduce. So, research family. Pancora is a research scheduler developed by Sarah Bird at UC Berkeley for her PhD thesis. She demonstrated the use of dynamic runtime resource utilization of each of the simultaneously executing application to better schedule and load balance process onto multi-core computers. Scheduler features. Certain resource manager and scheduler features are key and the primary intent of a large scale computing system and the nature of the job policies. There are many features that we can compare among these schedulers, and one of the most important features are described below. The features are explained with their impact on both HPC and big data jobs. Also, these features are organized into subsections as follows: scheduler metadata, job types, job scheduling, resource management, job placement, scheduling performance, and job execution. Feature comparison. We shall compare how the schedulers stack up against each based on their features. There are many overlaps and feature parity among the schedulers within each of the families. So we will explore the subset of these schedulers. We choose representative schedulers from each scheduler family. We have chosen so these are the following schedulers that we had chosen for our further evaluation. So they are IBM Platform LSF, OpenLava, SLURM, Grid Engine, Pancora, Apache Hadoop Yarn, and Apache Mesos. So as we can see the results from the paper, we have a fixed total amount of work and all additional time that it takes the cluster to execute, the total set of jobs decreases for the utilization of the cluster. So where n is the task per processor, and you can see a delta t here. This is Scrum measure, this is GE, and this is for Hadoop, and this is for Mesos, Apache Mesos. The previous figure shows the results of a launch latency as measured by utilizing defined among the approximate and more exact utilization models derived previously. In both cases, models qualitatively agree with the data and indicate they can be used as a reasonable approximation in theoretical utilization analysis. But even if we put any time, the scheduler consumes time in managing jobs, execution will decrease utilization. All the schedulers do well in 60-second tasks except for Hadoop Yarn. All the schedulers launch jobs reasonably fast. Hadoop Yarn has greater overhead for each job, including launching an application master process for each job. So if you see here, these are Scrum Grid Engine, Mesos performance similarity with 1 minus, 5 minus, and 30 minus seconds taken. Multi-level scheduling. A key to increasing the utilization for 1 minus 5 minus second job is to decrease the job launch latency or not launch as many jobs overall while still getting all the jobs done. LL Map Reduce is a tool that greatly simplifies the setup and execution of processing of many data files with the same program. It employs the MapReduce parallel programming model, which consists of two user-written programs, that is mapper and reducer. The input to the mapper is a file and the output is another file. The input to a reducer is a set of mapper output files. So first we have mapper and then we have reducer. The input to the mapper is a file, and that output is another file which is sent to the a set of output mapped files are sent to reducer. Using the multiple input and multiple output mode requires a middle modified map application that will read the input file with multiple lines of IO file names pairs. So here there is a comparison of scheduler latency versus number of tasks per processor with multi-level scheduling. So overall, when we see for this paper, there was a great work done by the authors on HPC and big data scheduling jobs. So coming to our conclusions, schedulers are primary component for scalable computing infrastructure because they control all of the work in the system and directly impact overall system effectiveness. Schedulers have many features, and certain features can enhance the execution of certain workloads. In this paper, we have compared number of scalable compute cluster schedulers, and we also have seen how authors have developed the concept of scheduling families based on their lineage and feature. We also got a chance to compare and contrast the number of key features and their impact on high performance data analytics workload. We found that in general, there are many features across the schedulers that are examined. We then focused on scheduler latency, creating a scheduler latency model, which was discussed in the paper, and also validating the model with a set of timing measurements on the subset of schedulers, which were SLURM, Grid Engine, Hadoop, Yarn, and Apache Mesos. We found that Hadoop Yarn performance was than the other three schedulers, and that the other three performed similarly. We then use a multi-level scheduling technique with the LL map reduced to tool to increase the overall utilization from slum, grid, engine, and messes. Scalable system schedulers for HPC and big. So this is the paper which we used as a reference. Thank you for giving me this chance. Uh, I would like to thank Professor Ziminglu for giving this chance to learn and explore about scheduling jobs for HPC and big